Today we're going to take a look at vector applications. And we're going to look at 3 or 4 problems here. So let's see, I'm going to go back up here and get the first one that we're going to take a look at. So the first one here, let's see. We have a car, a remote control car is initially at the point 3,2 and moves with a constant velocity of 2I plus 4j. Find the position of the car at any time. So our position of the car, well, where is it starting, would be 3, -2, plus I'll use a t for time, and our velocity vector would be 2, 4. 5, 10, when you see a velociraptor coming towards you, you run away with a velocity vector of 3I minus j. Write a vector equation to represent your position at any time. Okay, so 5, 10, plus, I'm going to put the t for time again, 3, -1. We'd have 5, 10, plus 3 times 3, -1. So 5, 10, plus 9, -3. So we would be at position 14, 7. Calculate our speed. Well, from this vector here, we know we're going over 3 and down 1. But our speed is actually that magnitude, because we're not going over and down. We're going to go that direct route. So our speed, 3 squared plus -1 squared, well, that's 10. So it would be the square root of 10, and we were at you. So let's see. So you're moving at 5, 10 plus t times 3, -1. This velociraptor is moving at 1352 plus t times 6, 8. So let's set this up. Our x is 5 plus 3t equals -13 plus 6t. So we can check here, when will our t's be the same? We add 13, so 18 plus 3t equals 6t, minus 3t, so 18 equals 3t, so t equals 6. And we're going to check our y's here. So our y's are 10 minus 1t equals 52 plus 8t, minus 10 minus 10, -1t equals 42 plus 8t minus 8t, so -9t equals 42. So t equals 42 over -9. So our time isn't the same, and you might be saying, well, this is different than what we did the other day. The other day we just solved for our variable and then plugged it back in. But we have to think about this. So here is, maybe you start here and your path is going this way. The velociraptor starts here and your path goes this way. So the paths cross, but this is like saying our x values, so they have the same x values here and here. So this is after 6 seconds. And the other one, -42 over 9, they have the same y values. So, the same y values, a couple different spots, but it's at, maybe if we looked at the height, here's the same height. But to intersect, that means at the same time they have to be at this x, y. And right now it's saying we're at the same x here and at the same y there, but we're not at that place at the same time. So the next one we're going to take a look at, let's see. We're going to take a look at some torpedoes here. So let's see, what do we have? 2 torpedoes. Write a vector equation for the submarines to intersect. They have to be at the same point at the same time. So we're going to look at our x's. So negative 5 plus 3m equals 5 plus 1m, minus 5 minus 5, negative 10 plus 3m equals 1m. So that would be negative 10 equals negative 2m. So m equals 5. And then our y's, 4 minus 1m equals 9 minus 2m. So the last one that we're going to take a look at, we have a position vector of boat A t hours after it leaves the harbor, and then we have a second boat and its position is given by that. How far are the two boats when they first leave the harbor? Well, when they first leave the harbor, time would be 0. So our first boat is at 0 times 30, 15. So our first boat is at 0, 0. Our second boat would be at 55 plus 0 times 10, 10. Calculator here. So you could figure that out and figure out how far away they are. So how fast? Speed is our velocity vector. So that first boat equals c squared and square rooted. And the second boat, 10 squared plus 10 squared, well, that's 200. So the boat's in danger of colliding. So plus 10 equals 5 plus 10t. So let's see if we solve this. So this would be 20t equals 50. So t equals 50 over 20. So minus 10t minus 10t, 5t equals 5. So t equals 1.